All right, so I guess we'll get started now, since it's a few minutes past the top of the hour. Good morning or afternoon or evening to everybody to our 8th RiskCan Compound Extremes webinar with two very exciting looking talks on drought, looking at them from two slightly different angles. And we just have a couple preliminary announcement type things here, and then we'll move into the talks, and then with the usual 20 minutes per talk with 10 minutes for Q&A, discussion, and so on. And then for anyone who's interested, we'll have 20 or 30 minutes again of just unstructured coffee break type time at the end in whatever format kind of makes sense based on whoever is left. See. Yeah, so I just wanted to point out there's been in the US a lot of news recently about this situation caused by widespread cold and snow in the US, and there's been a lot of news articles kind of specifically describing this as a compound event, particularly how it affected the energy sector, and then from there the water sector through frozen water pipes and so on. So yeah, hopefully there's interesting research on this in the coming years. So yeah, we'll have another coffee half-hour thing at the end. I also wanted to note that you've probably heard of these, but just to point out again, there's multiple other RiskCan groups, and Kai and I are thinking of having some joint webinars with them to kind of emphasize the overlaps. So I just put 4 of them that are kind of the 4 closest to compound events, in my view, roughly in order, I would say, of the connection. And you know, if you're interested in like being on the mailing list for one of these groups, you can find the info on the RiskCan website and sign up there. I think you don't even have to email anybody anymore. It's just a direct sign up. And then the other thing is, you may have received an email through the general RiskCan mailing list. I'm not sure exactly, but in any case, there's an ERL journal, a special issue coming up here on Earth system resilience and tipping behavior, which is inviting. So RiskCan is, as a whole, is able to have a number of invited contributions to this issue, and the deadline is in the fall. And there's a few papers from this invitation through the RiskCan, you know, about some aspect of resilience or tipping points that are starting to be planned at various levels of perspective versus more first-run data analysis. But there aren't any that are kind of specifically related to compound events and their cascading risks exactly. Some that kind of touch on it more briefly, but in any case, there's still a lot of room for someone to lead something or just join something that's already existing. So if you haven't already seen it and you have some idea about how to write something that'd be interesting for that issue, let us know, or Jana Stillman, who's kind of the point person between the RiskCan and ERL. Kai, do you want to add anything on that?
No, not specifically. I think yeah, it's a nice opportunity. Colin and I discussed a bit about this before the webinar started, and yeah, it would be great if there would be some contributions that take into account kind of a compound events perspective. I could imagine a couple of linkages to the tipping behavior and the resilience yeah, framework. So yeah, it would be great if people think about possible topics, and yeah, feel free to reach out in case you want any additional information on that.
Absolutely, yeah. All right, with that, I will stop screen sharing, or attempt to for a second, and turn it over to Kai to introduce Deepti.
Thanks. Yeah, and well,
sorry, I'm a little bit
I do this little introduction.
Yeah.
Deepti, feel free to
There we go. All right.
start screen sharing already. So yeah, it's great to be back from our little winter break with the second season, which starts off with 2 exciting talks on the larger topic of droughts, taking 2 different perspectives. And our first speaker today is Dr. Deepti Singh. She's an assistant professor in the School of Environment at Washington State University. And she received her PhD in Environmental Earth System Science from Stanford University. And before becoming a professor, she was a postdoctoral fellow at Lamont Doherty Earth Observatory of Columbia University. And yeah, she has worked on a variety of topics within extreme weather and climate research, including extreme event attribution, wet and dry extremes, the atmospheric drivers, specifically monsoon, but also mid-latitude circulation, and the societal impacts, such as water availability or food security. So really a wide variety, a huge spectrum of topics. And we're very thankful that she's with us today and that she accepted our invitation. And we're looking very much forward to your talk. As usually, after the talk, there will be a bit of time for questions. Just type them into the chat window and we will read them out, or we will call you up directly. So yeah, the floor is yours, Deepti.
Oh, thanks, Kai. I wanted to start with acknowledging my collaborators for the work I'm going to present today. Most of the work that I'm going to present is sort of led by my postdoc, Dr. Singh, and our collaborators on this work are Weston Anderson, who's at Columbia, Modisam Ashfaq, who's at Oak Ridge National Labs, Chris Skinner at UMass, and Vimal Mishra at IIT Gandhinagar. So I just wanted to start by kind of showing this map here, which I like to, I mean, this is just basically a map of our global wind patterns. And it shows that, you know, we have a physical process by which like weather conditions in different parts of the world are connected. And so most of my work is sort of inspired by understanding the connection between extreme events occurring in different parts of the world that are potentially connected by some sort of physical mechanism. Today, I'm going to specifically talk about droughts, but I thought I'll just use this opportunity to introduce some of the other work that's going on in my group related to compound events. So hopefully you don't mind me digressing for a couple minutes. So given that there are so many definitions of concurrent and compound events, I wanted to just start with defining how I define them. So generally, I think of concurrent extremes, which I guess are within the category of compound events, as the occurrence of multiple extremes at either the same location at the same time or in different locations at the same time. And there are lots of examples of that, as Colin just mentioned, as we've kind of just recently experienced one. 2020 also had similar examples of concurrent extremes where the Western US was experiencing severe heat and wildfires, while the Eastern US was being affected by hurricanes at the same time. And so these kind of, the compound extremes to me is really an interesting research area because, these events are not happening in isolation and there are physical processes that connect them on various spatial and temporal scales. So the overarching research questions that my group tends to address are trying to understand how have the characteristics of concurrent extreme events changed in recent decades. What are the physical drivers of different types of concurrent extremes? And how will these events and their physical drivers change with projected climate change? So there are basically 3 areas of concurrent extremes that my group is working on. And we're sort of motivated by improving the understanding of the physical drivers of compound events to aid in the predictability of these hazards and their impacts on human and natural systems. So the three kind of main areas that we work on are spatially concurrent heat waves. My postdoc Cassandra Rogers is working on that. You can see the map here that shows the type of events she looks at, which are basically heat waves occurring in multiple locations at the same time that are highlighted by the darker colors on this map. The other set of extremes we work on are concurrent droughts, again, spatially concurrent droughts affecting multiple regions simultaneously. And I'll talk more about that today. And then my student, Dimitri, is working on co-occurring air pollutants. So we're looking at both spatially and temporally co-occurring particulate matter and ozone, and the effect of both wildfires and meteorological conditions on the co-occurrence of air pollutants in the Western US. So yeah, this is just kind of an overview of the type of work that my group is doing. And today I'm going to focus mainly on the concurrent drought work. So the main question I want to address today is, what are the physical drivers of concurrent droughts, and how are they likely to change with warming? So this work was actually inspired by some work I did during my postdoc, which was focused on understanding the drivers of the late Victorian Holocaust, which were a number of famines that occurred in the late 19th century, with the worst ones being around 1876 to 78. This was a period when all the regions on the map that are highlighted in either brown or pink colors were areas that experienced drought during each of these years simultaneously. And these droughts were followed by severe famines that resulted in the famines in Asia, South America, and Africa that resulted in fatalities approximately 3% of the global population at the time. So about 30 to 60 million people. And it kind of was a pretty significant event in terms of shaping our society today. And so during my postdoc, I tried to understand what resulted in this kind of multi-year concurrent drought event. And what we found was that these droughts were, of course, associated with a really strong El Nino event, which by some measures is the strongest on record and is comparable to the 2016 El Nino event here. And but in addition to the really strong El Nino event, we also saw that the Indian Ocean dipole was in an extreme phase. It was the strongest positive phase of the Indian Ocean dipole, and extremely warm temperatures in the North Atlantic. And so this sort of record drought that occurred across these different continents were associated with the co-occurrence of extreme phases of multiple modes of natural climate variability. And so that's sort of what inspired the work that I'm going to talk about. I'm not going to go into details of what's shown on this map here. That was an event that occurred in the late 19th century, and we wanted to try to characterize the occurrence of concurrent droughts in the historical period, and understand what are the key drivers and how these different modes of natural variability affect the characteristics of concurrent droughts. So to conduct this analysis, we essentially look at 10 of the 27 regions that have been identified by the IPCC SREX report. So these are the regions that are shown in the map here. And the criteria we use for selecting these regions is that these are regions where predominantly there's summer season precipitation and there's high precipitation variability during the summer season. We characterize that by using the Shannon Entropy Index. And so all the regions that are in blue in these regions are ones that meet that criteria predominantly summer season precipitation with high monthly variability during summer season. And also several of these regions, not all, but several of these regions are connected by monsoon systems or affected by similar modes of climate variability. So that was kind of the motivation to study these regions together. And the metric we use for drought in this part of the analysis is the standardized precipitation index, which is calculated over June through September. And we define a region as experiencing drought, a grid cell as experiencing drought when the SPI is below 1 standard deviation of the historical variability. And we define a region under drought when the area, the total extent of drought within each region exceeds its 80th percentile. And that corresponds to about 21 to 25% of drought area within these individual regions. And then we specifically define concurrent droughts as events when at least 3 regions are simultaneously experiencing droughts. We consider 4 modes of natural climate variability. We consider ENSO, which we know is one of the major drivers of climate variability in the tropical and subtropical regions. We consider the Indian Ocean dipole, which is the difference in sea surface temperatures between these 2 regions. We also consider the tropical North Atlantic region and the Atlantic Nino regions, SSTs in all of these regions. Let's start with first looking at what these concurrent droughts look like in the historical record. So the gray line here shows the number of regions affected by drought in each year since 1981. Between 1981 to 2018, and we find that 11, there are 11 years when there were more than 3 or more regions simultaneously experiencing drought. And so most of you will recognize that there are 3 years with the most number of regions affected by drought are El Nino years. We also see that during these years, about 7 of the 11 droughts that have been observed have been associated with modes of variability other than El Niños. So there's El Nino events, but like, for example, in 1982, there was a positive Indian Ocean dipole, a negative phase of the tropical North Atlantic, and a negative phase of the Atlantic Nino. So what we decided to do next was to use the pre-industrial climate simulations. Because the observed record is relatively short, we used the pre-industrial climate simulations to understand the effect of these individual and combined modes of variability. The box plots here show the distribution of the number of regions affected by drought under each of the scenarios that are mentioned here. So we consider these phases because we found that in the historical record, these are the phases of these modes of variability that lead to the most number of concurrent droughts. With the CESM simulation, which is about 1,800 years long, we're able to get a sufficient sample size to sample size of events when only these specific modes of variability were occurring. And so the distribution here shows the probability of getting compound droughts. So sorry, the numbers here show the probability of getting compound droughts under each of these scenarios. And then the box plots on the right here are when these modes of variability co-occur with El Nino conditions. And so what we can see here is that, if we look at the if we look at the Nino conditions alone, there is the probability of getting these compound droughts is about 0.27. But if we consider when El Nino conditions occur with other modes of natural variability, the likelihood of getting compound droughts increases. And the largest increase we see is associated with the tropical North Atlantic the negative phase of the tropical North Atlantic. And there's approximately a doubling of the probability of getting compound droughts when these two conditions co-occur. We also see that the extent and the severity of compound droughts increases for when these conditions co-occur relative to when just El Nino events occur. So again, I'm not going to necessarily go into all the numbers here, but really the main takeaway is that when we, instead of just considering El Nino events, there is, we think that it's important to consider what the other modes of natural climate variability are doing as well. And so just to sort of summarize what we have understood about historical concurrent droughts, we find that there are 11 concurrent droughts in the last 38 years. El Nino is a primary driver of these concurrent droughts, but the co-occurrence of other modes of natural variability, some of which, whether or not they're independent is still debatable, but when these modes of variability co-occur, they can either amplify, they amplify the frequency, extent, and severity of these compound droughts. So next, we want to understand, well, are these compound droughts going to become more frequent and severe with projected warming? And so to do that, we use the NCAR CESM large ensemble simulations. We do that because the CESM ensemble it allows us to sort of explore the natural climate variability aspect compared to other simulations that have a smaller number of ensemble members. And so I think most of you are probably familiar with the CESM large ensemble, but I'll just give a quick introduction of that. So the CESM large ensemble basically has 40 members, and each of these members are identical, except for, they're identical in the forcing and the physics, and the only difference is the initial atmospheric conditions. So we use the historical simulations that have both the anthropogenic and the natural forcings, and we use the future scenario under the RCP 8.5 emissions pathway. And so just to give you an idea of what the model does, under the RCP 8.5 scenario, we see a warming of about 5 degrees by the end of the 21st century compared to the present climate. And so we look at the characteristics and the drivers of compound droughts at the end of the 30 years at the end of the 21st century compared to the 30 years at the end of the 20th century. And here, instead of using the SPI, we use the standardized precipitation evapotranspiration index because we want to capture the effect of temperature, which is obviously going to be important in a warmer climate. And so we use SPEI, and we really focus only on understanding the ENSO variability. We consider both phases of ENSO, the El Nino and La Nina phases, because when we looked at the longer observational record, we found that even though they're relatively few, La Nina events can also result in compound droughts. And so we wanted to compare the characteristics of these compound droughts under El Nino and La Nina conditions. So to give you the kind of main result here, we find that there's about a 60% increase in the probability of compound droughts by the end of the 21st century relative to the end of the 20th century. And these distributions here are, again, just the number of regions affected by drought in the historical climate and the future climate. We also find that the extent of drought as well as the severity of these compound droughts are exacerbated in the future. The increase in the extent and severity is of the order of about 10%. I think I forgot to mention how I define extent and intensity. Sorry, it's like 7 in the morning here, so I apologize for missing this important detail. So the drought areas we define as the extent of drought in all the regions that are experiencing compound droughts, and the drought intensity is the average SPEI across all areas that are part of the compound droughts. So we find increases in the frequency, severity, and extent of compound droughts in the future in a warmer climate, which is not surprising. So in trying to understand, what the drivers of these compound droughts, as I mentioned, we look at both phases of the, and we find, so if we look at the historical climate, in the CESM large ensemble, about 46% of concurrent droughts are associated with El Nino conditions, and about 22% of concurrent droughts are associated with La Nina conditions. Now, the characteristics of compound droughts during these conditions are different. So generally, if you look at compound droughts that occur during El Nino conditions, there are there are more regions that experience droughts relative to when there are La Nina conditions or non-ENSO drivers. So typically the ENSO conditions result in more regions experiencing drought, as well as, although it's not shown here, more severe drought occurring during those conditions. But that said, La Nina conditions also contribute to these concurrent droughts. So in the future, we see an increase in this concurrent droughts, and part of that is driven by an increase in the frequency of El Nino and La Nina events. We find that our results are kind of consistent with previous work that has shown that that both extreme El Nino events and extreme La Nina events tend to increase in the future. And we find that the number of compound droughts that are associated with El Nino events and La Nina events increase. So there's there's 60% more compound droughts in the future. The increase associated with ENSO drivers is about, sorry, I should remember that number. It's about 7. So there's 70% increase in ENSO-related compound droughts, even though the increase in El Nino and La Nina events is only about 22%. So this kind of suggests that, of course, the increase in El Nino and La Nina events are contributing to more droughts, but we also see an effect of warming, which is captured by the SPEI, that basically results in more compound droughts, even though the drivers remain similar. In fact, when we look at the teleconnections when we compare the teleconnections in the historical climate and the future climate by simply just looking at a correlation between ENSO index and SPEI, we see that the teleconnections actually remain largely pretty stable, but there is kind of a change in the location of where these droughts are occurring, partly because of changes in overall wetness in different regions and overall effect of warming on droughts in different regions. So I know I'm pretty close to the end of my time here, and I just wanted to share one more result. We also looked at not just how these droughts are changing, but we also looked at how the exposure to compound droughts is changing. And so I'll just kind of briefly summarize those results here. We looked at both exposure of agricultural areas as well as exposure of populations to these compound droughts. And we've looked at the exposure to both moderate compound droughts as well as severe compound droughts. And I'll just talk about the results of severe compound droughts for now. So if we look at the brown dots that are shown here, we see that in the present climate, the x-axis shows the area, the agricultural area affected per year in the historical climate, and on the y-axis we're showing the area affected in the future per year in the future. And so if we look at the total agricultural area that's affected by compound droughts, in the historical climate, that's about 0.07 million square kilometers, and in the future that increases by about tenfold. And similarly, when we look at population exposure, we see a pretty substantial increase in the number of people that are affected by compound droughts. And so for example, in the historical climate, there are about, in an average year, the risk of people being affected by compound droughts is about 10 million. And then if we look at different future projections, different population scenarios in the future, we see that the exposure of people to these compound droughts can increase from anywhere between 100 million people to 210 million people in the future. And so it's about a 10 to 20-fold increase in the exposure of people to these compound droughts.
Okay, yeah. So maybe Deepti, you can leave your summary slides up.
Yeah.
And we'll do some questions for 7 minutes or something.
Sure.
Thanks very much. Thanks very much for the talk. That was very interesting, and yeah, ties into a lot of other interests here on heat waves, food security, and everything like that. You probably didn't see, since we talked about the chat and how hard it is to see as a presenter. Jakob and Marcus both put in questions about sort of the bias of using SPEI and its tendency to overestimate temperature effects on drought. So I guess, what are your comments on that?
Yeah, so we didn't look at soil moisture from the models. We've looked at, we basically looked at SPEI and SPI. So they're not, we haven't compared, I know that there's lots of different drought indicators, but we looked at SPI and SPEI. And of course, when we look at just the precipitation index, we get slightly different results. We don't see as much of an amplification of the droughts when we're just looking at precipitation.
And so you still see an amplification though, or like how much does it reduce the change?
Yeah, we stopped using SPI a while ago, so I don't remember the results exactly, but I do remember seeing an increase in the frequency, but maybe not in the severity of droughts. But yeah, I don't remember those results. I can try to look at that, try to dig it up before the coffee session.
Sure, yeah, that can be a good follow-up kind of thing.
Yeah.
Then Farshad Pirani has a question. I'm not sure exactly what you mean by this, Farshad, so maybe do you want to come off mute and explain a little more? Perhaps. Anyway, so the question is, how do you relate a local teleconnection to the drought in the 10 regions?
I guess I can just maybe, so when we look at the teleconnection, I think we're just doing a very simple, we've looked at some of the other factors as well, but for what I just showed, we simply looked at the correlation between SPEI at each look. We've done both SPI and SPEI, and it remains relatively the same. When we consider, we just look at the correlation between SPEI and the ENSO index. So
locally, and then you add them up.
Well, the maps I showed here were just these are the correlations that are done at each grid point. So there are 30 years times 40 ensemble members, and for each ensemble member, sorry, for all that data, those 1,200 years, we estimate the correlation between SPEI and the ENSO index.
Yeah. So Wakar has a question, which I thought you actually covered. Did you look at changes in severity and extent in the future scenarios?
Yeah, we looked. We looked at the frequency, severity, and extent. And it looks like the extent is increasing, but I think the severity increases to a larger extent than the extent. Sorry, too many extents there. We basically see an increase in the area of concurrent droughts as well as the severity of concurrent droughts in the future. It's relatively moderate compared to the increase in frequency. So the increase in frequency is about 60%, whereas the increase in extent and severity is on the order of 10 to 15%.
Okay, yeah. I sort of had a question myself, which is about whether you or whether you've done this or whether you know of anyone who's done this, and that is looking at the interaction between the different teleconnections and their changes. So I guess the tropical North Atlantic and ENSO seem particularly I don't know, interesting to me, and I recall vaguely some work recently on how the Pacific kind of partially drives the Atlantic, but the Atlantic somehow has its own kind of motive force. And I don't know, maybe just comment on the state of knowledge of that.
Yeah. So in the first part of the analysis that I showed, where we looked at these individual drivers, we actually did look at how they are correlated, how the different indices are correlated, and there's certainly some correlation, like especially with the Indian Ocean dipole. It has a relatively high correlation with the ENSO index, and there's I think that's actually pretty well. I mean, it's not like it's not 100%, but it's I want to, if I remember the numbers correctly, it was close to like 0.4. The correlation can occur on these different modes can affect each other on different timescales. So we did find some correlation between ENSO and the tropical North Atlantic on like 6-month timescales. And so it looks like they of course do affect each other, but I think there's still like work to be done and understanding to what extent they do. I think part of the limitation is just that we have a relatively short observational record, but I want to say there's like a WCRP workshop going on, starting soon, on these interbasin interactions. So that probably have more details there. So there is some literature on that, and there are definitely connections between different parts of the different basins that we've considered here. And in the paper, we've actually discussed the level of correlation between the indices and talked about these teleconnections.
Okay, yeah, we have time for maybe 1 or 2 more questions, depending on how long they take. Jason Otkin has a question. Have you looked at preferred regional combinations based on ENSO state? I guess the idea is, so do you have the same patterns for the same ENSO kind of characteristics, or do they vary a lot between severe ENSO or something?
Yeah, that's a good question. We actually have done that in the paper. We let's see if I can. I don't know if I necessarily want to show a new figure here. We have looked at that, and the combination of regions, they remain relatively stable in. So maybe the question is about whether the difference between El Nino and La Nina events alone, right? Sorry, I'm just going to read that question again.
Yeah, Jason, if you want to clarify, maybe I bungled the idea of the question.
So we do actually quantify which, in our analysis, we've actually quantified which regions are likely to experience drought under El Nino and La Nina conditions. And then we also look at how that risk changes in the future. And so we do find some changes in the risk, like the monsoon regions tend to see a lowered risk in the future because it's primarily driven by wetting in those regions. And then we see more, like these regions here have a higher likelihood of being part of these compound droughts in the future.
Okay, yeah, thanks for the answer. That was nice. And that, I think that answers my question about it a little bit. Okay, I guess at this point we'll move on to the second talk. Thanks again, Deepti. And yeah, if people have more questions for Deepti and want to ask them in a smaller group and so on, please stay on for the coffee hour, and that's the idea of it. So our second speaker will be Jordan Christian from the University of Oklahoma. And Jordan is a postdoc there in the climate, hydrology, ecosystems, and weather group. And his work focuses on how flooding and drought are influenced by underlying land surface conditions, particularly topics of relevance to the Great Plains of the US. So yeah, Jordan, the floor is yours.
Awesome. Well, thank you very much for the introduction, and thank you for inviting me to give a presentation during this webinar. So yeah, what I'll be presenting today is going to be over essentially kind of a brief overview of my PhD work and work that's also kind of continuing over into my postdoc. So it's going to be covering basically anything and everything about flash drought, but with a little bit of focus on flash drought climatology, both regionally and also globally as well. And before I get going, first of all, just want to acknowledge the co-authors for all this work. First of all, Jeff Becerra, who has been my PhD advisor and is continued to also be my postdoc advisor as well, has been a part of all this work. And then especially Jason Ocken and Eric Hunt. Jason's up at the University of Wisconsin and Eric is University of Nebraska, and they've also been a part of this work during my entire PhD and also for many future projects as well. So just want to acknowledge them. So before I get into a giant quick mix of results over the last several projects we worked on, I first of all just want to give a brief 1 or 2 slide overview of what flash drought is and how it's defined. So first of all, flash droughts are different from conventional droughts in the sense that they are defined by their rapid rate of intensification towards drought. And so when we look at flash drought, they generally take place on the order of several weeks to a couple of months. And with flash drought are several associated impacts. The first and most immediate impact is a rapid depletion of soil moisture, but as the flash drought progresses and develops, rapidly start to see excessive moisture stress on ecosystems. Flash droughts can lead to devastating losses in agricultural regions, and following flash droughts, you essentially can get land atmospheric conditions that promote the development of wildfires as well. So many impacts associated with flash droughts. And we can provide word definitions of flash drought, but I really like to show graphically what flash drought looks like. So I have an example image here taken. This is taken in the central US back in 2012, where there was a major flash drought event. This image was taken from a pheno campsite back on the 1st of July. And we can see just 30 days later, in a very short amount of time, just a month, how rapidly drought conditions developed in this area. So if you need a graphical representation or visual representation, this is what flash drought looks like and how it's defined. So just a quick outline and overview of what I'll be showing today. This is going to go pretty quick, just going to kind of show a summary slide of some of the different research projects we've worked on over the last several years. But first of all, just want to talk about how we came up with the flash drought methodology and how it's interpreted. So that'll set the stage for some case studies, specifically looking at the 2012 United States flash drought, and then also 2010 flash drought occurred over southwestern Russia, preceding a major heat wave event. And then once I go through some of the case studies, then I'll move out. Start first of all looking at flash drought climatology, about 30, 40-year climatology over the United States, and then moving outwards globally to look at flash drought development as well. So with that, just a couple slides now on the flash drought identification methodology. First of all, the variable that we used is called the standardized evaporative stress ratio, or what I'll be calling a CESR for the rest of this presentation. So essentially, this is a measure of evaporative stress, and it's just evapotranspiration divided by the potential evapotranspiration. But what this variable represents is the overall stress of the environment. So it's a combination between the lack of moisture at the land surface and also atmospheric demand for that moisture as well. So what we do is this is a little specific information that isn't super relevant, but basically to calculate, we just take this evaporative stress ratio and we standardize it by subtracting out the mean and dividing through by the standard deviation to get that for any data set that we're using. But in terms of interpretation of how we view evaporative stress, take a little snapshot here back during 2012 flash drought across Oklahoma, where we're located. The red line is showing CESR, and what's showing here is generally when you have decreasing CESR values, this is indicating in a very general sense that you're leading towards drier and warmer conditions. And if you have increasing CESR, this indicates that you are approaching wetter and cooler conditions in a general sense. So this is the metric that we use to identify flash drought. And then just a very, very brief overview of our identification methodology. This was fairly comprehensive in terms of how we identify flash droughts. I have a kind of a summary schematic here. I'm not going to really go into that. What I want to mostly just talk about is we focus on two different kind of factors in the methodology. The first two is that we wanted to make sure we were grabbing flash droughts that have an emphasis on vegetation impact, so not just short-term dry spells that may not have much impact. But then secondly, and probably most importantly, is having criteria that capture that rapid rate of intensification. And this is what separates it from conventional drought. So that's the overview of the identification. So now I'll start kind of going through a mix of flash drought case studies. The first one's going to be 2012 US flash drought. Second one will be 2010 southwestern Russia. So let's start with the central US flash drought. So in terms of flash droughts over the United States, this is probably the primary one. This is the top flash drought event that's probably occurred in the past at least 20 years or so. And this is the primary focus it's been studied fairly well, especially over the past 2 or 3 years. But we took a deep dive on this case to look to see how flash drought developed across this region. And so just for starters, I have a drought monitor image here to indicate the drought conditions that occurred across this region. Image on the left is showing drought conditions in May. For the most part across the central United States, it was relatively clear. There was some drought in the southwestern portion of that domain, some, very just not even considered drought, just light drought conditions across some of the domain, but relatively, we're pretty good shape for that time of year. But as you can see on the right image, within a 5-month period, by October, the whole region had ended up in D3, D4 category, the worst drought categories. And if you were just going to look at these two images, you think, okay, drought developed over 4 or 5 months across this region. But one thing that's missing is if you look at flash drought, it actually tells a different story about how drought developed during this 5-month window. And so I will start by looking at how flash drought develops. So very briefly, what we use is a regional reanalysis data set. The resolution is about 32 kilometers, and we take this variable, CESR variable, we take the identification methodology, and we run through the methodology, and we can see where flash droughts develop on a grid point by grid point basis. And this is just supposed to provide kind of a first order approximation of where flash drought occurs. And so on this image, for example, this top left one is showing April. The red grid points are the flash drought or the month where flash drought development occurred for that specific month. And as you progress through these months, May and June, July, the black dots are representing flash drought development that occurred prior to that month. So we can see in April, the epicenter really started in Kansas. This wasn't just broad across the whole region. And as you progress through these months into May and June, July, you'll notice there's propagation that heads north and to the to the east and southeast, and eventually fills in through, keeps propagating northeast through the region. And by the end of the growing season, most of the region had undergone flash drought. The interesting thing about this case was that it was not just all at one time, as, for example, if you're looking at the drought monitoring, is what you would expect, but is a propagating event. And we can dig a little bit more into this by looking at some time series. So the best way to get oriented with these time series is this top left panel here is essentially the epicenter of where the first flash drought development started to occur. And as you move towards the bottom right panels, you're getting farther and farther away from the epicenter. And so you'll notice in this tan shaded region, this is where the methodology identified the flash drought development with respect to this evaporative stress variable. And you can see in north central Kansas at this time where the epicenter occurred, we had flash drought development start around the month of May or during the month of May. But as you progress outward from this epicenter, this Missouri is to the northeast or east of Kansas, and then Oklahoma is kind of to the south. You can see that starts to develop, but it's a little later than Kansas. And as we progress to panel D in central Nebraska, see development starts to occur later in the year, or later in the growing season, kind of through June. Getting farther away from the epicenter in Iowa starts to develop in July, and then eventually get all the way up into Minnesota and the surrounding states. And flash drought development doesn't begin until very late in the growing season in August. So the whole summary of this case is essentially that flash drought doesn't have to be just one giant event that just occurs over one region. It can be very complex, and it can spread, evolve, and propagate through a region. And so that was kind of the key takeaway I want to show from this specific case. So that'll conclude this case. So the second case now I want to talk about is a flash drought that occurred over southwestern Russia. And so just for the sake of time, I don't want to go too much into the background here, but essentially back in 2010, there was a major heat wave event that occurred in Western Russia and also portions of Eastern Europe. And this occurred later in the growing season around July and August. But what we wanted to do is we wanted to go back and look and see, did a flash drought occur prior to this event? And what does this mean with flash drought and its role in cascading impacts, essentially? And so this is just kind of a starter image here, kind of get oriented with this event. So on here is the color bar indicating kind of the flash drought start month for these pixels. We use a global reanalysis in this case to look at flash drought. And for the most part, essentially flash drought developed at the very, very latter portions of May and developed through June across essentially just in one broad shot across an area in southwestern Russia, southeast of Moscow. And so this is kind of just a spatial map. What I have here is a black domain where we essentially take an average of all the grid points to look at how this flash drought evolved temporally as well. And so I'm going to show that here and start to kind of tie it into this heat wave event that we saw across this region. So there's a lot on this graph. The main focus will be the Caesar line here in the red line, the tan region, which is where we identified flash drought, and then also the heat wave region identified in this orange color, where it's just simply defined where temperatures are exceeding 2 standard deviations above the mean. And so, it's first of all immediately apparent that we had rapid drought development in the month of June preceding the heat wave event. And one of the things we were trying to do is kind of relate these two events together. And you'll notice at the end of the flash drought event, this is actually very common with flash drought events given the land atmosphere conditions following flash droughts, but you'll notice the temperature line, which is in the brown, and the vapor pressure deficit, which is in the green, those start to spike at the end of the flash drought event. So, why didn't we see heat wave conditions start to develop right after the event? Well, can't go all into the level of depthness I need to explain this event, but essentially some rainfall occurred in the middle of their summer. It was just about 2 centimeters. It wasn't a lot, but it was enough to moderate surface temperatures, the vapor pressure deficit, and also you can even see a little response and spike in evaporative stress where the evaporative stress was declining on the environment, improved temporarily. But it wasn't enough because ultimately, as you can see, after the flash drought event, the land surface was essentially primed for heat wave development. So the rainfall temporarily moderated everything, and then we see a spike of the temperatures and vapor pressure deficit following the rainfall event. So these are kind of how these events were related temporally as well. But we also want to look at how maybe heat wave development propagated through this region as well. So basically everything I have in this domain here, kind of what I'm showing, underwent heat wave for the most part, especially north of 50 degrees latitude. But what I'm showing here is an image of vegetation index, enhanced vegetation index from satellite data. And the darker reds are showing below average vegetation conditions. Green will indicate above average vegetation conditions. And what we see is this image here taken in July. This is right after the flash drought event. And you can see for the most part, you know, most of the region is desiccated with respect to vegetation conditions. But over time, over about a month period, we actually see there's a propagation of vegetation desiccation, but also heat wave development through this region as well. So there's multiple studies that pointed to the broader region of heat wave development through this region. So essentially what we showed is this flash drought development that occurred in southwestern Russia primed land atmosphere interactions to promote heat wave development, and then this heat wave development propagated due to essentially advection of sensible heat up to the northwest towards Moscow and through a large portion of Western Russia. And so hopefully that does it justice. I wasn't able to go all in depth in this study, but it was a really interesting study. We have a summary figure here of kind of everything we talked about and looked at in this paper. If you start just on this top left section, this is focusing on the hydrometeorological features. We noticed there was a flash drought that developed concurrently with a quasi-stationary upper level ridge. And once this got going, we had some moderation of evaporative demand, but ultimately led to heat wave development due to sensible heat advection and land atmospheric temperature coupling. But that's the hydrometeorological side. With respect to cascading impacts, we noticed that flash drought played a key role in preceding a lot of these events. First of all, probably the most direct relationship is flash drought being directly tied to the immediate impact on vegetation stress. Ultimately, this led to an increased risk of wildfires, which led to an increased risk of air pollution. Ultimately, overall, with the excessive heat and everything that's going on, led to a major increase in human mortality, eventually devastated agriculture so bad, Russian government had to lead to an export ban. It was just incredible how much impact there was on this environment, all starting with kind of essentially an upper level ridge and the major flash drought event in just a small little region. And so, like I said, this was just the summary side, and there were several takeaways that we had from these two case studies, the US flash drought and also the Russian heat wave. The first one we noticed was that flash drought development can essentially occur in two ways. First of all is you can have this spatial propagation of flash drought where it starts at one area, and as you progress through seasons or multiple seasons, it starts to propagate outwards, and you have rapid drought development occur across a broad region over time. The second way we kind of see with the Russian flash drought is in a pretty large area, you can just concurrently undergo flash drought all at the same time. And essentially with both these events, primarily focus on the Russian flash drought, but what we found between these two case studies is, first of all, that flash droughts can lead to heat wave development. So this is done through, once you finish the rapid drought intensification on the environment, you can essentially get these land atmosphere interactions that prime excessive surface temperatures during heat waves, or at least it sets the stage for heat wave development. And the second thing was, especially that we saw in the Russian heat wave case, was flash droughts can provide a focal point for advection of sensible heat, which, for example, can lead and promote to heat wave development in other locations as well. So hopefully that the kind of looking at a couple of case studies kind of visually can show what flash drought looks like spatially and temporally. And now that we have an idea what that looks like, now we can start looking at climatologies with flash drought. So the first one we're going to look at is focusing just on the United States and the climatology as well. But I'm not going to spend too much on this because I want to focus on the global images. But what we did was we took this regional reanalysis with the 32 kilometer spatial resolution per grid, and we looked at about 37 years between 1979 and 2016 for the growing season, April through October. And we just identified any flash drought event that occurred across these grid points. And essentially what we found was a major hotspot across the central United States, which is indicated by the darker red colors. So one thing that's really important to notice is that these flash drought events are, they kind of co-align with major agriculture, at least in the United States here, as a large amount of production is over the central US, and that's where flash droughts primarily occur as well. So that's very important from the perspective of flash drought impacts in agriculture. We also notice there's regions as well where flash drought doesn't really tend to develop, at least from the viewpoint of evaporative stress. So first of all, you see that out in the desert portions of the Southwest United States, very low frequency along the Rocky Mountains, the mountainous regions, and also the Appalachian Mountains and the Ozarks, heavily forested areas. There's just not much flash drought development, and there can be several physical mechanisms that may be responsible for that. But what we do find is that the flash drought frequency, at least across the United States, was most common across agricultural belts, which has very large implications. And we'll notice that this is not just restricted to the United States, because now I'm going to zoom out here and we're going to take a look at global flash drought now. So just to provide a little bit of background for this.
Just on time, could you try to conclude in a minute or two?
Yeah, no problem. So yeah, let me skip this slide right here, and let me just go straight. I'm just going to show this one figure here, climatological global flash drought. And so you can notice right here, the darkest colors are indicating the highest frequency. And what we see is that the largest or most occurring regions with the most occurring flash drought occur over Brazil, India, the Sahel, Great Rift Valley in Africa, and so on. But there's also many local hotspots as well across the central US, Iberian Peninsula, Western Russia, as we just saw in the case study, and Northern Australia, and so on. And so we went, we went really deep into this. I have several figures here. I'll just skip over them for now, and we can talk about them after the fact. But essentially, we looked at the seasonality as well. We looked at these trends in flash drought spatial coverage, and essentially had several key takeaways here. Just once again, showing that flash droughts primarily occur in agricultural regions, which is very important from a food security perspective, and also saw several regions that also experienced statistically significant changes in flash drought spatial coverage with time during the 36 years we examined. And so, yeah, I will go ahead and leave it at that on the summary side and take any questions.
Thanks a lot. Really interesting talk. Very interesting framework. As usual, please either raise your hand or type your question in the chat so that we can either read it out or call you up. And to give you some seconds to write down your questions and think of them, I had a couple, and maybe just starting from a very technical point of view, I was wondering about the relationship between vapor pressure deficit and the standardized evaporative stress index that you introduced. Just on a very general note, you touched on that quickly when showing this case study of the 2010 heat wave, but I was just interested in general.
Yeah, and one second, I'm also going to stop screen share for a second because I was having some issues with the presentation mode, but I can pull that up if anyone references a specific figure. But yeah, in regards to the vapor pressure deficit in Caesar, so just in a very general sense, it can be a little complicated because Caesar, we're looking at a combination between moisture at the land surface, but also, the demand for that moisture. So generally, what we see with vapor pressure deficit is if it increases, this is indicating that you're leading towards drier conditions. So it should be pretty closely related to Caesar and just in an overall sense. So yeah, as vapor pressure deficit increases, you'll see that Caesar value decrease, which is indicating higher evaporative stress.
All right, thanks. I have a couple of more questions, but maybe I'll let the audience go first. And there's one question from Deepti. Do you want to just unmute yourself and ask it directly?
Sure. I was just wondering, you skipped over the slides, but I was kind of curious about what makes those global hotspots prone to flash droughts.
Yeah, let me go ahead. I'm gonna screen share real fast so I can pull that figure up again. All right, so actually, let me go into presentation mode here. So hopefully you all can see this. So I was gonna talk about this a little bit. So we have some ideas for why these events may be occurring more often compared to other regions. So, for example, the central United States has been heavily studied. And, we have several papers that have looked at that from our group and other groups and stuff like that. And we generally see, for example, upper level ridges being a common theme for these regions. But once you start to get into the tropics, it gets a little more interesting. One thing that we noticed right away that we had talked about in our paper as well is land atmosphere coupling. So kind of going back to those, those key papers showing where, land atmosphere coupling occurs most often. We see the central US pulling up, also the Sahel is a common region, and India. So those might be being related to flash drought development, as land atmosphere coupling has been tied pretty closely to flash drought development, but also monsoons as well. We're wondering if maybe monsoons have a role, especially if you go into, we believe during the transition windows when monsoons are supposed to begin, especially like in Southeast Asia and Northern Australia, if you miss that window or that window is delayed, maybe you have an absence entirely of a monsoon, and that's coupled with above average evaporative demand, you get kind of these hotspots of flash drought development here. So we discussed a little bit, there's several other regions as well. There could be teleconnections that are involved as well, and so on. There's so much involved here, but yeah, there needs to be several pathways that look into this to start kind of digging out some of these drivers and what regions may have more of an influence from specific drivers versus others. But yeah, that's a really good question.
From an impact perspective, I was wondering if there's like some specific impact that is specifically linked to flash droughts in contrast to like normal droughts. And usually drought conditions start to have an impact when they really, last for a long time. So that's more of a duration aspect to it. Is there also something that relates to the rate of change as you presented?
Yeah, and that's another really good question. It's like, what, we're looking at flash drought and drought, what's the difference, especially from an impact perspective? And if I had to pinpoint to one thing, a common theme that, every study focuses on is really agriculture. You get agriculture impacts from drought, but flash drought makes it so much more devastating just because it happens so suddenly and in some ways unexpectedly, and especially with crops during sensitive stages during the growing season. If you have a drought develop in just like a 4-week period, it can be absolutely devastating versus maybe a conventional drought that takes a whole season or more to develop. So maybe you have some time to help moderate those conditions a little bit. But yeah, that's the one key thing, especially we've noticed too with studies. Well, why agriculture is such a big focal point with flash drought is because of the fact that you can actually have above normal conditions. Everything can look pretty good. It's like, maybe you get a lot of precip and, soil moisture is looking great. And you're like, hey, I'm good. And the farmer's like, hey, I'm good for the next couple of months and stuff. But we've seen you can have very rapid development in just a short amount of time, even when conditions don't say otherwise. So I think that's the key difference between we're looking at impacts is, yeah, they may have similar impacts, but what we're doing is we're looking at timescales accelerated to very short windows, and that's where you can start getting very large losses from an agricultural perspective.
Interesting, yeah, thanks. There's one question, so we might have one question, time for one question left before we start the coffee hour part. Rasha, feel free to directly ask your question and unmute yourself.
Hi everyone, thanks for the presentation. Actually, I asked about the global flash drought figure. Why we don't see any indication about of flash drought in the MENA region? Like it is totally white.
Yeah, so basically any flash drought that's, can you hopefully, actually, let me share my figure one more time here. So if there's any flash drought or any regions that you're looking at, it's like it's very low or it's white. I should point out, I didn't get a chance to go through this, but all the white regions were essentially masked out if they were very arid. So anything that reached a certain aridity index value, they were just masked out, because we don't really look at flash drought in regions where there's already it's already really dry and you just can't get this arid subhumid transition essentially. And we also masked out grid points as well that were just too far north or south, that just were too cold to essentially have enough evaporative demand to get flash drought. So yeah, if there's a region that's if it's masked out, it's white, it's because it's either just too cold or just too arid for flash drought development, at least with the approach that we took in our study. And then yeah, any other regions that are very, very low frequency, it's probably going to be due to they're either heavily forested locations, they're up at high latitudes, they're up in mountainous regions, and there could also be several other explanations as well. But yeah, that's for the most part what we have looked at and found for this study.
Thanks. Yeah, really, really fascinating stuff. I would have more questions actually, but I will have to spare them for a coffee hour. And so for now, let's just thank the both speakers again, John, Christian, and Deepti Singh, for two very exciting and interesting talks, and for contributing to this webinar series here. So thanks again.